that we at least briefly looked at to introduce this whole chapter. What was that question? I think it was multiple choice number 3. It was the integral of secant of x, tangent of x, dx. We didn't do a sample exam. We talked about why we didn't do it. We weren't quite ready to do it, but I did want you guys to see like what it's going to look like, etc., etc. And this was the first integral question that showed up on the exam, and I told you guys what the right answer was. Do you remember what it is? Plus c. And we started introducing the idea of, hey, how are these two related? And what did you guys notice? Yeah, this function is the derivative of that function. Wait a minute. But why was there, or why is there? And why was there for a and b and c and d and e? Why was there a plus c? Because I don't know if there was a constant to begin with, because the derivative of every and any constant is 0. So the final answer to this, what we would call indefinite integral, because there are no numbers here, there are no what we would call bounds, that's coming, definite integrals are down the road a little bit, is we're asking ourselves, who is this guy the derivative of? Who is this guy the derivative of? And that was how we introduced and started forming the idea of an antiderivative. But yesterday we didn't just talk about the idea of antiderivatives, how we're going backwards from a derivative to an original function. And as you guys are doing the graph match, hopefully that's also helping you put into categories or into camps original functions and their derivatives, etc. But we also got the definition, your first forever card of the semester, forever number 27. That's been updated online. The definition of an antiderivative. This whole capital F, little f, it's one way of showing little f is what's being given to you inside the integral, but we need to think of him as the derivative of the antiderivative, of the derivative of the solution to the integral. We talked about the plus c and why he's necessary. We saw him in different examples. Talked a little bit about why there's a, why there's a dx in the integral. Talked a little bit about why there's a dx in the integral with the dy dx notation. But then we were like, hey, if it's derivatives backwards, then we look at some integration rules. Now, I had you guys yesterday take a picture of this, and I told you to write it all in your notes. Hopefully you did get it in there. If you still need a picture, you can go ahead and grab one. But let me go ahead and transition to the forever card specifically, and I want you guys to mark for yourselves which formulas are going to be forever number 28. Which cards are going to be forever number 28? Let me give you a second. If you have your forevers, you can grab them out technically and fill them in. It's not everything. If you guys notice, I believe this ends at the end of the trig, which means exponential and logarithmic will be another card. Exponential and logarithmic, even though it wasn't that big old table you just saw, that's going to be on another card. So let me give you a second. You can write these in your notes. If you didn't get the other ones written in, you can mark it as forever card number 28. You can write them in your forevers itself. But besides a few little things here and there, we're basically just going to start practicing today. And tomorrow we'll get some whiteboards and do some group competition. Well, some group work / competition. Because just like derivatives, we got to get good at the basic integration rules and start training our brains at going backwards. Backwards, not a crazy idea in math. You go backwards with addition and multiplication, division and subtraction every time you solve any sort of equation for x. You go backwards with inverse trig anytime you're given trig and you have to solve for the argument. You've gone backwards in foiling with factoring. The idea of backwards isn't crazy, isn't new. Just derivatives backwards, well, we're just not used to it right now. guys at least figured out which rules you need, right? Zero would be any constant.
Do you have 3 calculators you could borrow?
Uh-oh. You guys didn't come prepared with calculators, huh? Let's see. You don't want those ones. This is 1, this is 2, this is 3. Am I going to get him back?
Yeah.
All right. That one works. Oh, that one's solar powered. This one works. Here's 2. Let me see if I can get you a better one for the third one. There you go. You're welcome. There we go. This is just like the arbitrary constant here. It's like these plus these that you see other places. So it could be any constant. Does that make sense? Okay. Because the derivative, remember in our notes, I need to get out of full screen so that we can see it. But in our notes, this comes straight from the rule. The derivative of c is 0, so therefore the integral of 0 is c. Yeah. Now, all of these, or at least the ones that you just wrote down, they're not actually all strictly rules per se. Some of them are more just kind of like beginnings. Meaning, like that one, okay, the integral's answer is, the integral's answer is, the integral can be rewritten as. You guys see the differences with these two? Everything else gives you like an answer to the integral. These ones are just like the next step in the process. Like constant multiple, I can pull the k out, and he'll come in at the end, just like I did with derivatives. Or sums and differences, I can split them up, just like I would do with derivatives. So these ones aren't per se answers. These ones are instead steps to the process or steps that you can take. And then we have all of our trig that can go backwards. I warned period 6 about it. I don't know if we necessarily took tons of time to warn you guys about it, but with the trig rules, can anybody see what could get a little bit confusing? Besides like just needing to know, like, oh, secant squared comes from tangent. What else can get confusing with the trig integrals? What was our trick for remembering which ones were positive or negative with derivatives? All the c's, negative. What's the struggle with integrals? It's going to be backwards, right? Wait, no, it's not backwards. All non-c's are not So for integrals, any answer with a c has to be negative. Because the derivative of any c had to be negative, the integral that results in a c has to be a negative. Because the integrals are going to naturally be positive. Doesn't mean there can't be a negative in there. But the integral of sine, if I have a positive sign, it must have come from a negative cosine. Because, remember, how do we check any derivative rule? Sorry. I have to reorient my vocabulary. How do we check any integration answer? We have to derive it. Any antiderivative should be derived to get back where we started. So therefore, what's the derivative of cosine? Negative sign times a negative will be a positive. We're going to have to reorient our brains. Okay. The very last kind of, concept-y thing that we should add before we just start practicing. The harder ones. What I've said so far, antiderivative, we're deriving backwards. Antiderivative, we need to consider a constant. Technically, there is a term for that because antiderivative plus c is not just one antiderivative because c can be anything. It's an arbitrary constant, the constant of integration, plus 1, minus 13, plus pi over e. I don't know. So technically, it's not just one antiderivative. Technically, it's called an entire family of antiderivatives. And you're going to get an entire family of antiderivatives that you can only make particular or specific. You can only fill in with a specific constant if they give you an extra clue. A family of antiderivatives, aka including plus c, will come from or will be the answer to any indefinite integral. And I already alluded to this. I just didn't specifically write it down yet. That's any integral without bounds. And what I mean by without bounds, if I was to have you go find your calculator, which most of you couldn't find quickly, and go under math and find the integral function integrate, or go in your grapher, like your actual graph, and go find the integral button. If you were to hit it, it would ask for a lower limit and an upper limit. It would have a little box here and have a little box here. We've used it like once this year at the very beginning. And there are numbers that are filled in, a starting point and an ending point, and that relates it to area that some of you guys saw in the AP exam, the practice exam yesterday that we scrolled through really fast. That meaning, even though they're very, very tied together, is separate, is different. You will get an antiderivative or a family of antiderivatives when the integral does not have bounds. So the long story short, if we were to do something like the integral of one that we did yesterday, like 5x to the fourth, you guys remember who or what this antiderivative is? Good, x to the fifth plus c. Technically, that's not just one function. Now, it is a cubed function. If you were to look at the math dance back there, cubed functions all look like, or an odd function all look like this. If you have like pluses and minuses of different degrees, then it can start getting wonky in between, like some of your graph matches. But there's no plus or minus of fourth degrees, third degrees, second degrees. It's just a fifth degree. So it is going to kind of look cubic. However, it could be this one that goes through 0. But couldn't it also be shifted up 1? Couldn't it also be shifted down 1? Couldn't it also be shifted up 10? Couldn't it also be shifted down? So it's a whole family of antiderivatives. So every time you see this plus c, it's not just one function. It's technically all these different possible functions. Now, this is a very, very basic antiderivative. There are some anti-differentiation techniques that actually get you solutions that don't all look the same and aren't all vertical translations, but we won't see that until later because it kind of has to do with implicit backwards in a sense, and we haven't really dealt with complicated ones like that yet, and we won't for quite a while. So hang in there. We'll see weirder ones that aren't just vertical translations of each other, but the most basic ones where you have antiderivative plus c is equal to y. It's a whole family of all these different possible functions. At the bottom, something I've been referring to, you can only make c specific if you're given a specific clue. And number 2, something I've also alluded to with the word backwards. Derivatives and integrals do have an inverse relationship. The derivative of the indefinite integral, you're going to end up with f prime. You're going to end up with the integrand or the inside. There is an inverse relationship. When we start getting to definite integrals, it gets a bit harder. But for right now, a derivative and an integral do undo each other, which is one of the reasons that will go backwards with integration. Okay. With that, we've gotten some of the theory in. We've introduced some important ideas like the inverse relationship, like what's going on with plus c, and the fact that right now you won't ever know what that plus c is without some extra clues. But the most important thing for today that we want to get done is how to use these rules to antiderive or to integrate basic functions. So let's start with this one. Some of you guys, your brains will be like, oh, duh. Sweet, write it down, but don't say it out loud because other people's brains are just like, okay, there's a rule. Let's go look at the rule. So that's how I'm going to start off with it. But just a few of you, if you're already getting down the rule, you might be jumping to answers. Just don't say it out loud. Not yet. Rule. Why don't you guys look at that forever card that you wrote down? Which one can we use? We started here in derivatives too. There are 2 rules that apply. What's one? Got it. Do you guys see the K rule? If we have the integral of k times f of x dx, we can take the k out. Good, Ryan. That's one rule we're going to use. What's the other one we're going to use? X to the n ends up getting us what? Do you guys see how the power rule works? Every function comes from or was found from deriving a power, and deriving a power took away one, so I have to add one. And remember, we have to be able to derive and make it work. If you derive this, wouldn't that come down? And when that power comes down, I need it to cancel out. So over here, what can I do? First of all, I can say, hey, number 3, coefficient 3, let's pull you out. Step number 1, pull them out. Step number 2, 3 times x to the 14th had to come from x to the 15th, but if I take the derivative of x to the 15th, isn't it 15 x to the 14th? So divide by 15 and then maybe you're good. So I would get the 3 because it's a constant multiple, and then I would get the 15 comes down, whoosh, x to the 14th. Hey, I think this works. Except just like with derivatives, if you can simplify, please do. What's another way of writing that? Just so that you guys don't forget there are other ways of writing these. But yeah, Thomas, good. Either one, good. Dun 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 dun. Crazy? No. Take some practice? Yeah. What's different with this guy then? There's a sign, so there's going to be a trig something something. There's a 3, but we already dealt with a 3 up here, no big deal. That's going to be the k f of x. But there's also the square root of x. Let's not rewrite the k rule, because the k rule we just dealt with up here. Okay, no big deal, pull them out. But we are going to have to think about a couple rules down here, right? What's the integral of sine? Negative cosine plus e. Why do we not need any other new rules? How am I going to do the square root of x? Backwards power, right? But what do you guys think? Should we maybe rewrite it first? Can we rewrite it to be x to the 1/2 dx minus 3 times the integral of sine? Wait a minute. What other rule did I just use and I didn't really say anything about it? I did use the k one, but we kind of referenced that. I haven't used this one yet, but we're going to. Yeah. What's the integral of f of x minus g of x? What are you allowed to do? Take them one at a time, which you guys got used to with derivatives, but I'm just showing you I am following the rules. So ready, set, apply the rules and check in your groups and see if you got it right. Go. Apply the rules. Check in your groups and see if you get it right, or if at least you guys all line up. Crazy thing for just a few of you, if you never got the derivative rules down super solid, it's possible that if you work hard with integration, you'll not just be able to integrate, but you'll also be able to derive better. Because for quizzes and tests, man, it will be nice for you to know whether or not your answer is correct for every indefinite integral you ever face. If you derive it and it matches, theoretically, you're good. I don't want you guys to be going blind, so let me give you the final answer. I won't give you the in-between steps, and I'll have you guys discuss as I start showing the in-between steps as to whether you got it right and why you might have gotten it wrong. One version of the final answer would be 2/3 x to the 3 halves plus 3 cosine of x. plus. Go, check in on each other. How far did you get? Check in with each other. How far did you get? And do you have the in-between step? Three over 2 is the power. But on bottom would be divided by 3 over 2. And when you divide by 3 over 2, you multiply by the reciprocal, which makes sense for deriving, right? What do we need? Dividing by 3 over 2 would be multiplying by 2/3. But the deriving makes sense, right? A number by its reciprocal is 1. Did you guys notice what else was a little weird? Just a few of you might have thought like, oh, he has a plus C and he has a plus C. Did anybody have 2 plus C's? Oh, maybe not. If we had done that, if you had done separate plus C's, you would have had plus some arbitrary constant and then plus some other arbitrary constant, because they don't have to be the same. They can be different. So I'd have to actually name them 2 separate things. But if you have some arbitrary constant and sub-arbitrary constant, like even if we knew what those numbers were, guys, what could you do with 2 constants? Put them together to make a new constant. So instead of like actually showing all this work and being like, oh, C1, C2, you're a C3, hey, we just call it plus C. Does that make sense, Nick? Not unless there is a direction or a purpose. So for instance, if this came from words and they told us acceleration and we wanted to get to velocity, we would only take 1 integral. But if we wanted to get to position, we would take 2 integrals based on the context of the problem. But according to the problem, 1 integral was asked for, so 1 integral was solved and we have to stop. Just kind of like derivatives, you have to look at the prime or the double prime. And in this level of calculus, we won't ever see a is a thing, just not now. Makes sense? So what this is asking for with 1 integral is 1 integration done. But if it was something like a physics problem, we had to go from acceleration to position, 2 integrals would be necessary. Cool? Oh, sorry. Any more questions on either of these 2? I just assumed we were good, but that's kind of not very nice. Okay. Wait! Ah! Yesterday and the day before, I don't remember which day it was, sorry, one of them, I said something like there is no quotient rule for integration. What does that mean? Rewrite. Perfect. There is no quotient rule for integration at all. No quotient rule. None whatsoever. So we'll have to deal with quotients when they come. But for right now, try to rewrite, because I'm giving you this problem telling you that it fits the rules that you've seen. And technically, what happens? F of x minus g of x. Integral of x to the n plus 1. Those are the only rules you need. But how? There's a division. How did you guys rewrite it? That's one way. We could think of this as 3x squared minus 2 times x to the negative. Could rewrite this as a distribute. Or you could distribute the division which could have also come from multiplying 1 over x squared times 2. I don't know if your brain? Which one makes more sense? But all of them lead you to the exact same place of doing division divided by x squared with both terms, because you would have to distribute with the -2 exponent, or you would have to divide both, or you would have to distribute to both. But either way, what expression, or any of the ways, what expression do we end up getting? The integral of 3 minus. Wait, it's a division. Oh wait. Couldn't it just be a power? Now, I'm not done, but does the rewriting make sense? If you divide 3x squared by x squared, it's just going to be 3, so I need to integrate 3. And if you divide 2 by x squared, it is 2 over x squared, but that is 2 to the -2. We can't do division. The only division that we can do right now is the integral of 1 over x alone, because what's the integral of 1 over x alone? ln. We technically haven't written that in our forever cards yet, because there's going to be an exponential logarithmic section coming where we can deal with that separately. We can deal with him, nothing else with him. So over x squared, not ln. Ooh, I should have written one more rule. Why am I saying that? Because he's just a constant. If he's just a constant, where do you have to come from? Does that make sense? So the integral of k is going to be kx plus c. Constant multiple, the -2 is 1. What do we do with x to the -2? We add 1, of course. You're reorienting your brain. You're not deriving, you're integrating. You're not bringing down, you're going up. And we end up with 3x minus x to the -1 over -1. Isn't that going to be a plus? It's going to be minus a negative. 2 divided by -1 is -2. Does this make sense? Hopefully the answer is yes, but here's the problem. Do you think that's how the original function actually looked? There's a nice fraction up there. Are they going to have negative exponents? Probably not. So what's that now possibly mean? Integral simplified? Do you guys see how that's the answer, and that's the answer, and that's the answer? Remember how they can rewrite? How to get from here to here, from the second one to the third one. Yeah. Common denominators, yeah, cool kids? Are you going to have to work on making it match again? But what was the key to solving this at the very beginning? Realizing there is no quotient rule and rewriting. What do you guys think? We have 5 minutes. Ready, set, go. Letter C is a little bit of a cheater because it has to do with ease, but maybe you can do it. You're allowed to reach out to anybody in your group if you get stuck at any point. Go back to that table over and over as you're still getting used to problems. Show as much work as you need. Some of you tried to go too fast, too quickly with derivatives, and it ended up messing you up. Go slow and steady to win the race right now. We'll speed up as you get better. Check in your groups. How they doing? How are you doing? Anybody stuck? Do your answers match up? Ready, set, go. Collaborate. Ready for the answers? Where did I put my remote? I'm holding the little sound one. Oh, there it is. What you think? If you don't agree with me, take the derivative of mine. Does it match up? Bring down the 4, whoosh, x cubed. Ha! Bring down the 2, whoosh, x to the 1. Ha! 5. 0. Done. Derivative of tangent. Secant squared. Derivative of cosecant. Negative cosecant cotangent. Derivative of c. 0. Whoosh, done. Derivative of 3e to the x. Derivative of 4 ln. 4 over x. The in-between parts would have been x to the 3 plus 1 over 3 plus 1. X to the 1. And you could even do 5 x to the 0 plus 1 over 0 plus 1. There are some in-between steps, but not a lot. My last question to you, because you need to get started on this homework. How would you do this? There's no product rule either. Write it. How? Multiply power. Bye, guys. See you later. Alligators. Start playing with integrals tonight. Struggle. Because I would rewrite it to be integral of 3e to the x plus 4 integral of 1 over x. Does that make sense? Ellen. Yeah. Well, there's the rule that says the integral of k is kx, but you could also just see like, oh, it's x to the 0, add 1.
Then how did you get half?
Oh, from here.
Oh, okay. So, wait, on the top is